Number 3. Is this part of a pre-calc course or a calc course?
No, it's calc.
Okay, good.
I think, yeah.
You're headed on, presumably pretty soon, to differential calculus and then integral calculus.
Great.
Well, not as hard as it sounds. It kind of depends on what part you're in. Calculus is like a lot of math in that they certainly can start you off with some of the most difficult material for the whole course. Limits aren't it, but when you first get into differential calculus, you are going to be faced with some of the most difficult stuff of differential calculus. But it does get easier. I guess that's the one solace you can take. All right.
And actually, I set number 1 and number 2. It's at the very bottom. I don't know why it's set out of order. So maybe start there and then we can jump back to the top.
Okay. All right. Let's see if I can get number 1 centered on here. Now, can you read these? I mean, you've got it in front of you, so you can probably figure it out if you can't read it from my screen.
Yeah,
I'm
I can
not
read
sure
it.
I know how to blow it up because it's part of the email. It's not a file attachment.
Oh.
I don't think I have the ability to download it and manipulate it. Let me see if there's any things on here that lets me download it.
Next time I can download it as a PDF beforehand. So maybe that'll
if you can attach it as a file,
yeah,
it's a little bit
I
better because then I can actually get control over it. I can rotate it. I can zoom in, zoom out. When it's like this, I'm pretty much stuck with what you're looking at, which I can read it. And
I can read it too.
You probably have the original in front of you or not?
Yes, yes, I do.
Okay, cool. I'm just reading the title. Okay. State each x value at which f is continuous. So what's the first one? Starting from the left.
Is it -4? Or?
No, it's actually continuous at -4. Notice that I can draw right through -4 without lifting my pencil. I don't have to lift my pencil until I get to -2.
Oh, okay.
Okay. So, yeah, when I say starting from the left, this top one says smallest value, the fourth one says largest value, so they definitely want to go left or right. Okay. And continuous from the right or continuous from the left or neither, that's neither. In other words, it doesn't matter if I'm heading towards -2 from the left or I'm heading towards -2 from the right. I believe it's neither. Go ahead and put in -2 and neither. Does it didn't give you an answer till we answer all 4 of them?
No, I can.
Go ahead and submit it because this is a little.
Yeah, that's right. Okay,
good. All right, what's the next point of discontinuity going from left to right?
Is it 2?
Yep. Okay. And is that continuous from the right or continuous from the left or neither?
Is it from the left?
I would say neither. It's exactly the same situation as the previous one. In other words, it's a jump discontinuity. I wasn't quite sure what they meant as far as this continuous from the right or left. That's kind of a new concept. for me. But I think that they probably mean at endpoints only.
Okay.
But I'm not certain. That's why I wanted you to check. Go ahead and put in 2 and neither here and see if that's correct also.
No, that's not correct.
Put in 2 and continuous from the right.
It's continuous from the left.
Really?
Mm-hmm.
Is that a closed dot or an open dot right there from the left?
They're both open.
Well, the top one looks closed. That one's closed. But you're saying it's open from the left there.
Yeah.
You sure the first one was neither?
Yeah.
Wow. I do not understand how the first one could be neither. And
it says that.
What's that?
Oh, okay. It starts with -4, and then it's neither, and then it starts with -2, and it's continuous from the left.
Oh.
I didn't see
Why
that.
is it discontinuous at -4? Because, there's an open circle there that I can't see.
Oh, yeah. There's an open circle.
Okay. So let's start back at the beginning.
Oh, okay.
So
Yeah.
I couldn't see that. So -4 is the smallest, and it's neither. It's not continuous from the left or the right.
Mm-hmm.
And then the second one would be -2 and continuous from the left because the closed dot is there, so I can go up to that thing right there. Is that correct?
Okay. Yeah.
And then, why are there only 4 of them? There should be 5 because we got one at -4, -2, +2, oh, and 4. 1, 2, 3, 4. Yeah, okay. So the second one was -2, continuous from the left. The third one should be what?
2, right?
And what kind of continuity? Probably from the right.
From the right.
Wherever the closed dot is, that's coming from the right.
Okay.
So I'm going to say the third one is 2 and continuous from the right. And can you check that?
Yeah. It is 2 and continuous from the right. Yeah.
Okay, now I get what they're talking about. And then the fourth one is what?
4.
And
continuous from the right as well.
Correct.
Right.
That's an aspect of continuity that I don't get questioned about very often, oddly enough. Okay, number 2. State the intervals on which the function g is continuous. I like the way they call it g, but they label the vertical axis y. They should have labeled the vertical axis g of x. So let's see. I guess we can just go through these one by one, right?
Mm-hmm.
I mean, we know number 2 isn't right because there's all kinds of discontinuities there. It certainly is not continuous from -4 to 8. But number 1 has promise. It's continuous from -4 bracket, because it's closed dot, to -2 parentheses, because it's open dot. And it's also continuous from -2 to 2. So that's not correct. So let's look at the third answer. That goes from -2 to 2, parentheses on both sides, and then bracket from 2 not to 6. There appears to be a vertical asymptote at 4. In other words, it's not continuous where my cursor is right there, right?
Mm-hmm. Right.
Okay, so that's going to leave us number 5 as the only possible answer. And number 5 gets the first 2 intervals correct, gets the third interval correct, which is 2 bracket because of closed dot, 4 parentheses because it goes off to infinity, combined with 4 to 6 parentheses on both ends. There's no closed dot on either end. Can't count that closed dot there. And finally, the last interval is 6 to 8 paren on both sides. So it's definitely fifth option here.
Okay.
Let's go back to number 3. Okay. Domains. Remember something about domains, and that is it's all about what x cannot be. Not so much about what x can be as much as what x cannot be. Well, if I look at my enumerator, what can x not be? Can it be negative?
No, it can't be. No, it can't be negative.
X.
Okay.
The domain for that is x has to be greater than 0. Okay? Now let's look at the denominator. Well, the denominator is a quadratic, meaning that I need to factor it, because just always assume that when you're looking at a quadratic, you need to factor it. When I'm factoring quadratics, first thing is I split up the x's. They can only be split up like that. Second thing is I determine both signs. Both signs have to be opposite. In other words, it's either plus minus, but because this 3 is not the same as the coefficient for that x, minus plus might also be a solution, and I have to consider both of them. Now, 1 doesn't have very many factors, so I'm going to try 1 there and 1 there. Does that produce the middle term that I'm looking for? Remember how we get the middle term? That's plus 1x. In other words, we do the inside and the outside of FOIL. Minus 3x, add those together, I get minus 2x. Well, that's not our middle term, but it's close. It's the right number, wrong sign. So when you see that, merely move this one down to the negative sign, this one down to the positive sign, and erase the other, and this will give you the same number, opposite sign. Notice. In other words, that's minus 1x, that's plus 3x, that gives us plus 2x. So that's the correct way to factor that problem. Now, what restrictions does this place on x?
X, it has to be greater than,
That's
or
just,
it can't be -1. Oh.
Remember what's the first rule of math?
I don't know.
Well, if you want an interesting exercise, go on Google and say the 10 commandments of math, and you'll get 10 different lists, but every one of them will start off with the same first commandment. Thou shalt not divide by 0. Remember that.
Oh, right, yeah.
That's huge because that means that neither that nor that can be allowed to be 0.
Mm-hmm.
Okay, well, what does that mean? If this can't be 0, what can x not be?
0.
No, if x were 0, that would be -1. So what you do is you take that factor and you set it equal to 0 and solve it. And you end up getting x equals 1/3. Okay, so x cannot be 1/3 because if x were 1/3, we'd be dividing by 0. The other thing that x cannot be is -1. In other words, we're going to set that equal to 0. And that means x cannot be -1. Well, we kind of knew that restriction in the first place because the numerator told us that x had to be greater than 0.
Right.
Okay. So if we, okay, so they want interval notation. So we're basically looking at all real numbers except negative numbers and 1/3.
Okay.
Which answer is that?
What do you mean, which answer?
Well, there's 5 multiple.
Oh, sorry. Oh, yeah. Sorry, I didn't realize. I was looking at the wrong
If
one.
x can be all real numbers except cannot be 1/3, and it cannot be any negative. In other words, I can erase that. This covers all of the negatives. It's got to be greater than or equal to 0. Excuse me. It could be 0. You can take the square root of 0. You just can't divide by 0. And you can't take the square root of negative numbers. So here's the two things that x cannot, those are the restrictions on x. So the question is, which answer is that?
Is it B?
Yeah, in other words, it can be 0 to 1/3, including 0. It cannot be 1/3 in combination with 1/3 to infinity, and it can be every one of those. So answer B is correct.
Okay.
Every time I do that, I just got it to blow up. Now the question is, what was that, 3?
Yeah, that was 3.
Oh, okay, now I get it. Okay, I can do it. You don't have to send it differently next time. I've just finally figured out how to zoom in and zoom out on it. Use continuity to evaluate the limit. What's a better way to evaluate the limit? I'm not sure exactly what they mean by use continuity, but there's only one spot for an answer, so if we can come up with the answer, that's all we need, right? Well, what happens to this function as x goes to 4? What do you get when you substitute?
You get 14 and then
14 divided by
8.
It's the square root of 6.
4.
The numerator is 14. Denominator is the square root of 16, right? 12 plus 4 is 16. So the denominator is 4. You always want to simplify your ratios. So 7/2. And by all means, when you put in these answers I'm giving you, let me know if I've given you the wrong one.
Okay. Yeah, they've all been.
They puzzle me a little bit by what they mean by use continuity. I guess using continuity is the same as using substitution. I don't think I need to do anything other than substitution here. In other words, we do not get 0 over 0, so substitution is a perfectly fine way to find the limits.
Okay.
Did 7/2 work?
Mm-hmm.
Okay. Let's go to 5. Now we get harder, huh? You noticed when I was looking at these? Not really. What we have here is a piecewise function, okay? And the piecewise function is equal to that whenever x is less than or equal to 5, and it's equal to this whenever x is greater than or equal to 5. So for this to be continuous, what would have to be true?
It'd have to be less than or equal to 5.
No, both functions would have to be the same at 5. I'm sorry, I wrote that wrong, but doesn't matter. I thought it was a little odd that they were both greater than or less than or equal, and they weren't. However, let me draw a potential function for you. Okay, the left thing is a quadratic, so it might look like something like that. Okay, you with me?
Yeah.
The right thing is a cubic, and if it looks like that, it's not continuous, right?
Mm-hmm.
If the cubic looks like this, it's not continuous.
Mm-hmm.
What makes this continuous? What would make it continuous?
If it extended from 5?
Yeah, in other words, if the cubic does that, and it's a closed dot because that's greater than or equal to 5, now I can draw the entire function without lifting my pencil. That's what continuity is. So it's only going to be continuous if at 5 they're equal to one another. Well, let's set them equal to one another and do the algebra. So we have cx squared plus 2x has to be equal to x cubed minus cx when x is 5. Well, let's plug that in. C times 5 squared plus 2 times 5 equals 5 cubed minus c times 5. Now we have one equation, one variable, c. All I have to do is solve for it, and I'll have the answer. Now, let me expand that out a little bit. What do we have here? We have 25c plus 10 equals 125 minus 5c. So I'm going to move my 5c to the other side, and I get 30c. I'm going to subtract 10 equals 115. C is equal to 115 divided by 30. At a minimum, they're both divisible by 5.
Mm-hmm.
Top is 23, and the bottom is 6. Now 23 is a prime. That's got to be the answer. In other words, you always know you have simplified it when you get one number as a prime and the other isn't a multiple of that. In other words, if the bottom were 46, then I could simplify it to 1/2. But if your prime is the bigger number, well, then there's no way I can divide anything into both 23 and 6, because 23 is prime. Right. Nothing divides into 23 except 1 and 23.
Mm-hmm.
Okay, so 23/6, as unlikely as that sounds, should be the answer.
Yes, it is. These are much easier than than I thought they were.
Well, they're actually much easier than I thought, too. When I first looked at them, I thought they were harder. Let's see. I need to... the one thing it won't let me do... If I blow it up... Yeah, it won't let me go down below that one. So I'm going to have to go back to this page and scroll down to number 6. And now let me write this out so I know what they're talking about here. X squared minus 4 over x minus 2 whenever x is less than 2. And it's ax squared minus bx plus 1. Why are some of these numbers in red? Any?
I don't know, honestly. This is like a whole new system. I've never used this before.
And then it's 4x minus a plus b whenever x is greater than or equal to 3. Now notice the domain is continuous. It goes from negative infinity to 2 to 3 and then greater than 3. So it's negative infinity to infinity. It covers all of those. Now it says find the values of a and b that make it continuous everywhere. Okay. Well, where does it have to be, where do the functions have to be equal and to what?
They have to be equal or greater than 2.
Function 1, function 2, and function 3, just so we don't have to keep spelling it out. Function 1 has to be equal to function 2 at 2. Again, let me see if I can explain this conceptually. Here's 2. Here's 3. There's basically 2 vertical bands here. The function is this everywhere in this area here. And that's the way you want to think about it. Okay?
Mm-hmm.
But that's x minus 2 divided by x plus 2, which becomes x plus 2. So that's basically a straight line. Hold on. That ends somewhere at 4. In other words, it goes through, has a vertical intercept of 2, has a slope of 1. So that part of the function goes to there with an open circle. Now, the blue and the green that I've drawn are not necessarily asymptotes. In fact, they're not. The only reason I drew them was to give you an idea of how to think about piecewise functions.
Mm-hmm.
Okay? The second function is a parabola, correct? It's a quadratic?
Right.
Okay, quadratics, obviously for it to be continuous, it cannot do this, right?
Mm-hmm.
In other words, it has to leave off from this point right there. So I know that that quadratic has to look something like this, with a closed dot, because it begins when x is greater than or equal to 2. So if the quadratic looks like this, I at least have continuity at the point 2, right? On the x-axis. Mm-hmm. It's easy to get confused as to what somebody's talking about, the x or the y-axis here. So I generally try to spell it out. But at the x value of 2, these two functions have to be the same.
Okay.
So the first function, as I said, if I factor that and cancel, I get x plus 2. Okay. So basically I have to say x plus 2 has to equal ax squared minus bx plus 1 when x is 2. Okay, so what does that give me? 4 equals 4a minus 2b plus 1. True equation. I'm going to call that equation 4. Now, the problem with this equation is all by itself, I cannot solve for a and b. I've got only one equation, two variables. But the second point is going to let me come up with another equation in a and b, at which point I will have a system of equations in two variables, and I'll be able to solve it. Now, the equation 3 is linear. It's 4x minus these two numbers. That's linear. But it's whenever x is greater than or equal to 3. So for it to be linear, it's got a big slope of 4. It's got to look something like that. But the key requirement is that at the point 3 on the x-axis, the two functions 2 and 3 have to be equal to one another.
Okay.
You with me? All right. So if I say that ax squared minus bx, this is function 2, plus 1 has to be equal to 4x minus a plus b. For it to be continuous, that would have to be a true statement. And it has to be true when x is 3. So if I plug in a 3 for x here, I get 9a minus 3b plus 1 equals 12 minus a plus b. So that's my equation 5. Between equation 4 that has two variables, a and b, and equation 5 that has two variables, a and b, I'll be able to figure out what a and b are. So let me turn both of these into standard format, which is both variables on the left, the number on the right. So I'm going to rewrite number 4 as in the following way. 4a minus 2b, I'm going to move that 1 to the other side and get 3. You with me?
Mm-hmm.
Now I'm going to do the same thing on equation 5. I'm going to put my a's and b's on the left. Well, I got a total of 10a minus 3b minus another b is minus 4b. And if I put all my numbers on the right, I get 11. So there's my equation 4. There's my equation 5. I now have a system of equations that I can solve by elimination. Whenever you have them in standard format like this, elimination is always the best, easiest way to solve it. Okay? Well, I can't eliminate a variable as it stands right now, but what if I take equation 4 and multiply every piece by minus 2? That gives me minus 8a plus 4b equals minus 6. So that's my new equation 4. Now I've got it perfect. By adding equation 4 and 5, I'm going to eliminate b. Okay, gives me 2a equals 5, a equals 5 halves. And now I can go back and substitute a of 5 halves into the simplest equation, which is this first equation 4. And I get 4 times 5 halves minus 2b equals 3. Well, that's 10. So I get minus 2b equals minus 7. B equals 7 halves. A equals 5 halves. B equals 7 halves for number 6.
Okay, this is starting to come back, like elimination and stuff.
Yeah, you're going to find that there's a lot of algebra in calculus. In fact, there's a lot of algebra and there's a lot of trig. And there's some geometry. There's not a lot of geometry, but there's enough geometry that you really have to know all 3 subjects to be able to get very far in calculus. Okay? The key here was knowing that when I graphed it, it has to be continuous. So I can't have a graph that looks like this. That wouldn't be continuous. The only way it can possibly be continuous is if that point is on the same place as that point when x is 2, and if this point is on the same place as that point when x is 3. And that's what I did to generate those 2 equations. Was I substituted x of 2, setting number 1 equal to number 2, but that didn't let me solve it. But then when I set number 2 equal to number 3 when x was 3, that generated that second equation, and now I have 2 equations and 2 unknowns, and I can solve it.
Okay. That makes sense.
And part of that first equation there, x squared minus 4 over x minus 2, recognize that as something you're always going to be able to simplify because the top is different from perfect squares, which means x minus 2 times x plus 2. And so it's going to cancel out with the bottom. Still leaves a hole at 2, but notice that at 2, the equation is the middle one. It's not the top one. All right, let's have a look at 7. Use the intermediate value theorem that show there is a root of the given equation in the specified interval. Here's what the intermediate value theorem says. I'm trying to get from that point to that point, and I have a continuous equation. It has to go through all points in between. There's no way. In other words, if that point were, say, 1, and that point were, say, 6, there's no way for the function to be able to get from 1 to 6 without covering every point between 1 and 6. And I'm talking about on the y-axis. No matter how I draw it, I can draw it like this. I can draw it like this. I can draw it like this. The red, the black, and the blue each have a y value somewhere in their function that is every single point between 1 and 6. That's what the intermediate value theorem says. You cannot get You can't get from 30 miles an hour to 70 miles an hour without going through 50 miles an hour. It's impossible. You can't jump instantly from 49 to 51. You have to gradually go through it if the function is continuous. Now, obviously, if it wasn't continuous, well, then I could do something like this. I could do this. Now notice that it doesn't go through any values between that block right there.
Mm-hmm.
So it's only if you have continuity that the intermediate value theorem applies. You must have continuity. So let's see. So you have to say what f of 1 is and f of 2, and you have to say what you're going to select here.
Yeah.
What are your options? Let me push on that. Can I push on it? Will it show me the option?
No.
And
I don't, because it's just a screenshot. It's defined, continuous, negative, or positive.
It's how many choices? 4?
4.
Defined, continuous,
yes,
negative, or positive.
Yeah.
Well, it's not negative or positive. It's definitely continuous because there's no place that's not defined. But it's also defined. Choose continuous. Will it tell you whether you're right or not?
Yeah. Yes, it's continuous.
Okay. It's also defined, so I'm not sure where you would answer defined instead of continuous. Oh, I see. If it was not continuous, then it might still be defined. Okay. Okay, now f of 1. How do I get f of 1?
You just plug it in, right? Or substitute.
What do you get?
So you get 1 plus 1 minus 9.
Okay. Which is?
So, negative 7. Oh, wait.
I get 1 plus, yeah, that's right, negative 7.
Yeah, okay.
Yeah. And f of 2 is what?
It's 6. Is it 16? Is 2 to the 4 16?
Yes, it is. So
Plus
16
2
plus 2 is 18 minus 9 is 9.
9, okay.
So that goes there. And what's the last part? Since minus 7, I'm not seeing anything to the right of that. Hold on, let me open my... Oh, yeah, no. Since minus 7 is less than something which is less than 9, open that up and tell me what your options are.
It's 0, and then, so I don't know what you call these other signs. It looks like an E, kind of. And then it's 0, and then I don't know what that is. Like 2 signs I've never seen. Or I've seen them, I just don't know what they are. I can send you a picture really fast on my phone.
If you could, I can probably figure out what those signs are. I'm trying to think what they might be. Since my...
I just sent a picture to your phone.
You sent it to my phone?
Yeah, is that okay?
Don't think I'm going to be able to read it.
Oh.
I didn't get anything, but whenever anybody sends something to my phone, I'm never able to read it. I'm not sure why.
Okay, I can
send it to my email? Okay. Have you sent it yet?
Yes, it's sent.
And you're sending it to David Cowan, 1949?
Yeah, it's sending now. Might just take a second.
Okay. Just let me know when it says sent, because it's not
Okay.
going to show up on my end until it says sent on your end.
Yeah, it's being slow.
Was this email from you at 3:27? I never saw this.
Oh, that's not me.
That's not you? What am I?
No, I'm Morgan Harrison.
Oh, that was Morgan Thomas. My goodness, I never
Yeah.
realized I had so many Morgans. Okay, sorry. Let's see.
Right, it's still sending, so I wonder my email or my Wi-Fi is just sometimes the school Wi-Fi is very slow.
Well, let's see if I can figure out what it means. Got -7 is something, which is something 9. And it's got a less than, and then that's a greater than, and then there's something in between them.
Mm-hmm. Here, I'm sending it from my computer. Oh, there we go. My computer is much faster.
So the answer is probably 0. But no, why would that be an answer here? In other words, why would that be one of the options inside the thing? There it is. Oh. Wow. Have they, and question mark is one of the answers? No.
No, that was just what's in
It's
there.
either, what that is epsilon and delta.
Oh, epsilon and
So
delta. Okay.
0, epsilon, or delta. It's definitely 0.
Okay.
There is a limit definition called the epsilon delta limit definition.
Uh-huh.
You want to come across something hard, take a look at that sometime.
Okay.
I'd be amazed if they force you to deal with that. So was 0 correct?
I don't have any more submissions, so I'm going to wait. But I can check once we fill it all out.
Okay. There's no way it can be epsilon or delta.
Yeah, we've never even talked about that. So.
No. Okay, so let me go back open the older thing again. Oh, and then there's a second part to that also.
Mm-hmm.
Oh, there's a number C in the interval such that f of C equals, what are your options here?
It's 9, 0, epsilon, and -7.
Okay. Such that f of C is equal to 9, 7, 0, epsilon, or delta?
No, not even delta, just epsilon. But -7, 0, and 9.
0
Mm-hmm.
should be the answer.
0, okay.
For both of those. And is there more to the right? Thus,
No, that's it.
Is there still more?
It says, thus there is it says discontinuity limit root of the equation in the interval 1, 2.
Let me think for a second. This equation between 1 and 2, it goes from -7 to 9. So let's draw what that's going to look like. Okay, here's -7. Oops. And up here, let's make that 9. Okay. And between 1 and 2 on the x-axis, we know that if we graph that, it's going to start there, it's going to end there. You with me?
Mm-hmm.
And it's continuous between there. I mean, it might do a lot of things. This is a quartic, so it could do something like this, but I know it's continuous. And the way I drew it, it doesn't look like it would pass the vertical line test, so it can't be quite drawn like that. Here, it is a function, but it could easily look like that. Okay?
Okay.
Now, what the intermediate value theorem says is that if this is a continuous function, and it hasn't told us that it is, but I know that it is. If I were to graph that, it would be continuous. There's no points between between 1 and 2 where x is not defined. It's defined everywhere on that closed interval between 1 and 2.
Okay, so it's
and
continuous.
We figured out that f of 1 is -7 and that f of 2 is +9. Since -7 is less than 0, which is less than 9, now I'm beginning to wonder if the epsilon delta isn't applicable. I don't think it is. I'm almost, it's not applicable. So yeah, I'm pretty sure 0 has to be the answer for that one. There is a number c in that interval such that f of c equals, your choices again?
For f of c?
Uh-huh.
It is 0, 9, -7, and epsilon.
Well, it's 0 again. But
yeah.
we also know it could be -7 because it's closed interval. Oh, no. Notice that they put parentheses around that interval.
Oh, yeah. Okay.
Okay, as opposed to the original interval, which was a closed interval, which means we actually included 1 and 2 in the interval, whereas this does not include 1 or 2. But you can't get between -7 and 9 without going through 0, correct?
Mm-hmm. Right.
Can you get between -7 and 9 without going through -7? Yes, because it's an open interval. It may only be -7 at 1, and 1 is not in this interval. This interval is between 1 and 2. So it has to be such that f of c equals 0. What's the rest of it say?
By their intermediate value theorem, thus there is it says discontinuity, limit, or root of the equation.
A root.
Root, okay.
So we should have 0 there, 0 there, and root.
Okay.
For the third one. And notice that they even added their interval was open interval at the very end.
Yeah, that's all right. That's all correct.
Cool. Now, these are actually easier, the graphs. Interesting. But as I said that, give us this one. So they want me or you to draw this first graph so that it's continuous. I'm going to hold it. Sketch the graph of a function that is continuous except for the stated discontinuity where there's a removable one at 2 and there's a jump discontinuity at 4.
So I think we just have to pick which one represents.
Oh, it's multiple choice.
Yeah.
Oh. Well, that looks like the first one on the left. Let me look at the second one. The second one has a, here's what, on the lower left, that's what removable discontinuities look like.
Okay.
So if there's a removable discontinuity and a jump discontinuity looks like this one at 4. Okay. So, and also I would call that a jump discontinuity. So the top left appears to have both of them are jump discontinuities. The top right has a jump discontinuity. That's not it. The bottom left, that messed up my thinking. These must be called removable discontinuities here, which means not this one. It's got to be the upper right. In other words, the upper right has a removable discontinuity at x equal 2, because there's a hole there, and it's a jump discontinuity at 4 because it's jumping from this all the way up to there. See if that's
okay.
Right. Is that correct?
It is.
Okay, good. Morgan, I do have a 5 o'clock, but I think we're done, aren't we?
Okay.
Oh, no, there was one more.
I have 2 more, but yeah, it's okay.
Well, unfortunately, I got 2 minutes here. Hold on, let me take a quick look. Find the left hand and right hand limits at the given value of a. In other words, a is 1. So if I approach 1 from the left, what's the function equal
to? Less than 1?
No. In other words, I'm going to use this function when I'm approaching it from the left, the top one, right?
Yeah.
Because it's only equal to e to the x when x is less than 1. So if I'm approaching it from the left, I'm on the e to the x function. Okay, and where is it headed? Well, when x is 1, it's headed to e to the 1.
Okay.
So that's the first one. The second one is, what is the limit as we approach 1 from the right? Well, that's the bottom function. So if I were to graph x cubed and hop on that function and approach 1 from the right, my function would be equal to 1. So e for that and 1 for that.
Okay.
I know.
And I'm going to have to run, unfortunately.
Okay, that's fine. Thank you.
Yeah, you're welcome. Terminology is a little different in University of Alabama compared to Colorado, but basically it's pretty much all the same.
Okay.
Okay? All right, Morgan.
Thank you.
Bye-bye.
Okay. Bye.